Welcome to the deep dive. So, for years, scientists have been really grappling with a huge question about our universe.
Yeah, a really fundamental one.
Just how fast is it expanding? And, it wasn't just idle curiosity. There was this persistent kind of puzzling disagreement in the actual measurements.
That's exactly right. You basically had two camps, methodologically speaking. One looked way back, deep into the past of the ancient universe, and got one number for the expansion rate.
Okay.
But then when scientists looked closer to home, more present day, they kept getting a different number.
And that difference was a big deal.
Oh, huge. Because if both numbers were truly right, it pointed to a serious problem, maybe even a crack in the standard model of cosmology.
Our best blueprint for how the universe works, basically.
Exactly. It suggested our fundamental understanding might be, well, incomplete.
It really felt like a cosmic mystery was unfolding, challenging everything. But now things might be changing. There's new data.
There is incredibly sharp data, actually, from the James Webb Space Telescope, JWST. And it's giving us a fresh look.
And possibly resolving this whole thing, making the numbers line up?
It certainly looks that way. The conflicting measurements might finally be starting to reconcile.
Okay, so that's what we're diving into today then. We're going to unpack this whole puzzle.
Right. We'll explore the different ways scientists measure the universe's growth, try to understand why it's been so tricky, especially measuring it locally.
And then see how this amazing new telescope, JWST, seems to be, well, clearing things up.
Yeah, and showing that maybe the standard model is holding up okay after all, at least on this front. The research we're focusing on brings together data from both Hubble and JWST, led by Professor Wendy Freedman, a key figure here. It just came out in the Astrophysical Journal, May 27th, 2025.
Okay, let's dig in. The puzzle. You said two main ways of measuring led to this tension. Can you break those down a bit?
Sure. So method one involves looking back, like almost to the Big Bang itself.
Wow, okay.
We study the faint afterglow, the cosmic microwave background, the CMB. Analyzing its patterns gives us a very precise measure of the expansion rate back then in the early universe.
And that number was?
Around 67.4 kilometers per second per megaparsec. And the uncertainty is tiny, just plus or minus 0.7%. So very confident about that early value.
67.4 plus or minus 0.7%. Got it. That's the ancient history view. But the other way, looking closer to us now, that was the troublesome one.
That's where the headache really was, yeah. Measuring the expansion rate today locally is actually, perhaps surprisingly, much harder.
Harder? Why is that? Seems like nearby should be easier.
You'd think so, but it involves figuring out two key things for galaxies relatively close to us: how far away they are and how fast they're moving away from us, and accurately measuring those immense cosmic distances. That's the tricky part.
Right, okay. It's not like you can just pull out a cosmic tape measure. So how do they do it? What are the tools?
Well, they use things called cosmic yardsticks, or maybe a better term, standard candles.
Standard candles, like a standard light bulb.
Exactly like that.
Yeah.
The idea is if you know the true inherent brightness of an object, its wattage, basically then you can figure out its distance just by seeing how dim it appears to us.
Ah, okay. Fainter means farther away if you know how bright it should be. Makes sense.
Precisely. So you need reliable objects out there with a consistent intrinsic brightness.
And what serves as these candles in space?
Several things. A really important one for this work is a specific type of exploding star, a type ES supernova. They're thought to blow up with a very, very consistent peak brightness.
Okay, supernovae. What else?
Well, this new research, building on Professor Freedman's earlier work, also uses other types of stars. She helped pioneer for this, like certain kinds of red giant stars, and also carbon stars. They also have predictable brightness levels.
Interesting. So find these stars or supernovae in galaxies, measure how bright they look, calculate distance, measure the galaxy's speed, and boom, you get the local expansion rate. But you said there were big challenges. That led to the discrepancy.
Yes, several big ones. First, there's just stuff floating around in space between us and the cosmic dust.
Right, dust.
It blocks and dims the light, so you have to correct for that very carefully. If you get the dust correction wrong, you'll think the star is farther away than it actually is.
Okay, so dust is hurdle number one.
Then you have to be really, really sure these standard candles are truly standard everywhere, across billions of light years in cosmic time. Are they exactly the same brightness intrinsically way out there as they are closer by? Any subtle differences?
Good point. Checking the consistency of your yardstick.
Exactly. And finally, there are always tiny uncertainties from the telescopes themselves, the instruments. You need incredibly precise calibration to account for those little quirks.
Okay, so dust, potential candle variations, instrument effects. It sounds like trying to measure something precisely through, like, a foggy, slightly warped window.
That's not a bad analogy, actually. And yeah, all those factors historically meant the uncertainty, the error bars on these present-day measurements were just bigger than for the CMB method.
Which allowed for that apparent disagreement.
Right. But this is where JWST really steps in. It's kind of a game changer for exactly these problems.
Okay, so how does Webb cut through all that? What makes it so much better for this particular job?
Well, JWST, it's Hubble's successor, right? The most powerful infrared space telescope we've ever built. And its capabilities hit those challenges head on.
Like what specifically?
For starters, its resolution is about 4 times sharper than Hubble's. So it can actually pick out and measure the brightness of individual stars in distant galaxies that just look like blurry blobs to Hubble.
Resolving individual stars instead of smudges. Okay.
Plus, it's way more sensitive, about 10 times more. But maybe the absolute crucial advantage here is its infrared vision.
Infrared light. Why is seeing in infrared so key for this?
Because infrared light slices right through cosmic dust much better than visible light does. Co-author Barry Medor said JWST lets them see through dust that has, quote, historically plagued accurate measurement of distances.
Okay, so it basically removes that foggy window problem you mentioned.
Largely, yes. By seeing through the dust, they get a much truer measurement of the star's brightness, slashing a major source of error. And because it's so sharp and sensitive, they can find and study these standard candles in more galaxies than before. They more than doubled their sample size for calibrating supernovae, which gives a big statistical boost.
So a clearer view, better rulers, and more data points. Sounds like a recipe for a better measurement. And did it lead to a new number for the local expansion rate?
It did. Using this combined improved data from both Hubble and JWST, Freedman's team recalculated the present-day Hubble constant. Their new value is 70.4 kilometers per second per megaparsec.
70.4. Okay, and what's the uncertainty on that one now? Is it smaller?
It is significantly smaller than previous local measurements, although still larger than the CMBs. This new 70.4 value comes with an uncertainty of plus or minus 3%.
Okay, let's compare. Early universe CMB, 67.4 plus or minus 0.7%. New local JWST Hubble value, 70.4 plus or minus 3%. How do those stack up now? Does that 3% uncertainty make them compatible?
Yes, that's the key finding. While the central numbers themselves aren't identical, 67.4 versus 70.4, their uncertainty ranges now statistically overlap.
Explain that a bit. Overlap.
Well, the CMB range is very narrow because its uncertainty is so small, right? 67.4, 0.7%. The new local measurements range is wider, 70.4 myriad 3%, meaning it could plausibly be anywhere from about 68.3 to 72.5. That wider range includes values that are consistent with the narrow CMB range.
Okay. So before, the ranges might have been completely separate, suggesting a real conflict. But now, JWST's precision has shrunk the uncertainty on the local value enough that the two ranges touch or overlap. They could be the same underlying value.
Exactly. They are now in statistical agreement, given the current precision. That 3% uncertainty, while not pinpoint, is a huge leap forward for local measurements, and it seems to resolve the statistical tension that existed before.
Wow. Okay, so it's like we finally got glasses sharp enough to see that two things we thought were definitely different might actually be consistent after all.
That's a good way to put it. The improved clarity is making the difference.
So what does this agreement mean for the big picture, for our understanding of the universe? What's the main takeaway here?
Well, as Professor Freedman put it, the big takeaway is that this new evidence is suggesting that our standard model of the universe is holding up.
Holding up meaning it works.
It seems to, at least regarding the expansion history described by these measurements. For years, scientists have been looking hard for cracks in the standard model areas where it might break down, places where maybe new physics related to dark matter or dark energy might be revealed.
And this Hubble constant discrepancy looked like a really promising crack.
Oh, definitely. It was one of the biggest tensions in cosmology. People wrote literally over 1,000 theoretical papers trying to explain why the early and late universe measurements disagreed, often invoking really exotic new physics.
But if this new data shows they do agree, statistically speaking,
then it implies that the discrepancy probably wasn't a sign of new physics after all. It increasingly looks like it was an issue with our measurement precision. particularly with those difficult local measurements, dealing with dust and calibration.
So the universe wasn't necessarily behaving unexpectedly. We just weren't measuring its current behavior precisely enough to see the consistency.
That appears to be the strong implication from this work, yes. JWST provided the necessary precision, especially by tackling the dust problem, to bring the local measurement into line with the early universe prediction from the Standard Model.
That's fascinating. So a potential revolution in physics might just turn out to be needing a better telescope.
It really highlights the power of improved observation, doesn't it? It's a classic part of the scientific process. Sharpen the tools, sharpen the understanding.
So this particular cosmic detective story seems to be heading towards a resolution, reinforcing our current model. But this isn't the absolute final word, right? The team is doing more.
That's right. They're not stopping here. They plan to use JWST again next year, looking at a different patch of sky, the Coma Cluster, a huge collection of galaxies.
Why the Coma Cluster?
It provides an independent check, using potentially different methods to measure the Hubble constant directly, maybe without needing supernovae as an intermediate step. They're hoping to nail down the value even more precisely. Professor Freedman sounds optimistic about improving accuracy further in the next few years.
So the quest for ever greater precision continues. Each step sharpens the picture, either confirming this agreement or maybe revealing something new at an even finer level. Incredible stuff.
Absolutely. It's a really dynamic time for cosmology.
It really makes you think, though. If this major Hubble tension, this discrepancy that seemed like such a solid lead, wasn't actually the clue to finding those elusive cracks in the Standard Model, the ones that might point us towards understanding dark matter or dark energy. Well, where else should scientists be focusing their search now? What's the next big mystery to probe? Something for you to mull over until our next deep dive.